So in this video, we're gonna just get started on hydrostatic pressure. And hydrostatics basically means that the fluids have no relative motion. So it's pretty obvious that all fluids exert pressure. Now, fluids isn't limited to just liquids like water. It's also describing things such as air. So there are a few different kinds of pressure, and on Earth, there's this thing called atmospheric pressure. So atmospheric pressure is the pressure on the Earth's surface, and the pressure is a result of the air's weight above the surface of the Earth. So that means that on the Earth, let's say this is the Earth. The closer you are to the Earth's surface, the pressure will be greater because there's more air above you. So if you're on the Earth's surface, let's say the pressure equals 101 kPa. But if, let's say you're on top of Mount Everest, the pressure will be less than 101 kPa because there's less air above you. So gauge pressure is the difference between the measured pressure and the local atmospheric pressure. So it basically doesn't consider the atmospheric pressure. So all you have to really remember for this last kind of pressure, called absolute pressure, is that it's the sum of the gauge pressure and the atmospheric pressure. That's pretty much it. So in this example, we have a container that's filled with oil and water, and the oil is less dense than water, so it floats on top of it. So what we're trying to find out here is the gauge pressure at points 1, 2, and 3. And the first thing we can assume is that the pressure at the bottom of the tank, so at point 3, will be greater than the pressure at the top. So the absolute pressure at point 1, since it's on the surface of the tank, is the same as the atmospheric pressure. So therefore, the gauge pressure at the top of a tank or at the top of a liquid is always 0. So again, the gauge pressure on the surface of a liquid is always 0. So at the top of the liquid, the absolute pressure is equal to the atmospheric pressure. And this is because it's just open to the atmosphere. So the gauge pressure, if you remember from before, is just equal to the absolute pressure minus the atmospheric pressure. So the gauge pressure is 0. So the first thing that's important to remember when you're calculating pressure is that pressure equals the density of the liquid multiplied by the gravity constant multiplied by the depth. So the greater the depth, the greater the pressure, right? And that makes sense because the pressure at point 3 is going to be greater than the pressure at point 1. And that's because there's all this liquid on top of point 3, so there has to be more pressure. So that means that the gauge pressure at point 2 is going to equal the pressure at point 1 plus the density of oil, since point 2 is just under oil, times the gravity constant times the depth, which is h1. The issue is that we don't know what the density of oil is, but that's okay because the question gave us the specific gravity of oil. So basically, specific gravity is the density of the substance that you're trying to find the density of, divided by the density of water. And this is really important to remember because the density of water is equal to 1,000 kilograms per cubic meter. So if we know the specific gravity of a given substance, we can find its density. And in this case, the specific gravity is less than 1. The specific gravity of oil that it gave us is 0.8. So we know that the density of oil is less than the density of water, and that's why it's floating on top. So if we put this in on our calculator, we'll find that the density of oil is equal to 800 kilograms per meter cubed. So if we fill these numbers in, we'll find that the gauge pressure at point 1 is 0, and then we're going to add the density of oil, which is 800 kilograms per meters cubed, multiplied by gravity, which is 9.81 meters per second squared, multiplied by the depth of oil at point 2, which is 10 meters. So if we just put this in on our calculator, we get 88,000 290. Now, one thing that's super important in fluid mechanics is the units. So let's figure out what the units are. So if we cancel out the meters, we're left with kilograms per meter times seconds squared. So if you remember, the unit of pressure is a pascal, and a pascal is a newton per meter squared. And the SI units of a newton are kilogram times meter per second squared. So if you have a kilogram times newton per meter squared, so if you have a newton per meter squared, then you're simply left with a kilogram per meter times seconds squared, which is exactly the units that we got before. So the units of the gauge pressure are going to be Pascal. That was just kind of an FYI, but now you know why the formula for pressure is the density times the gravity times the depth. So this number 88,290 is kind of large, so we'll just simplify it to 88.29 kilopascals. So now we want to find the gauge pressure at point 3. And to do this, we'll do the exact same thing that we did before. So the gauge pressure at point 3 is the gauge pressure at point 1 plus the gauge pressure at point 2 plus the density of water multiplied by the gravity times the depth. So if we plug this in on our calculator, we will get 0 plus 88,290 plus the density of water, which is 1,000 kilograms per meter cubed, multiplied by 9.81 meters per second squared, times the height of the water, which is 12 meters. So plugging this in, we get 206,010 pascals, or 206.01 kilopascals. So that's how you would find the gauge pressure at these 3 points. And as you can see from this question, the deeper you get, the greater the pressure is because of the liquid on top.